Quality control is a real hot item now. Everyone's talking about quality. The big question is, do they really have quality, or they just talk about quality? We're going to talk about what's done in quality control, both here and in Japan, and we'll see what's going on a little bit. Okay, quality control is really made up of two pieces: process control and specification control. And that we're gonna talk about those things in the big picture. We're going to look at the big picture. Process control. A process which normally has a mean mu and a standard deviation sigma. What does that mean, first of all? How can I say mu and sigma? Don't I mean x bar and s? Well, yes and no. The reason I say it has a mean mu and a standard deviation sigma is because I want to imply that I pretty much know what the mean and standard deviation of my process is. In fact, let me describe what's going on. We have a machine. And this machine has been producing parts. Process is the manufacturing of something. And I've been producing something for quite some time now, and I know the average of all the things that I've produced. Well, if I have thousands and thousands and thousands of things that I've produced, and I have an average of that, the distribution is quite small. The law of large numbers says, hey, you pretty much know what the expectation is. So you know what the mean of the distribution of your parts is. Your process has a mean, and you pretty much know it. The standard deviation, the same thing. As you get a larger and larger number of observations in your sample, your estimate S gets closer and closer to the true value sigma. So since we have thousands and thousands, we pretty much know, to within a decimal place or two, what the mean and standard deviation are. And so the process has been going on for quite some time. We've been manufacturing our cars for years, and we know how things are going. So our machinery is moving. We know the mean. We know the standard deviation, mu and sigma. And we want to know, is that machine out of control or not? Well, it's considered to be out of control. That is, the machine is out of control if an observation is outside the 3 sigma limit. That is, outside the interval, the mean plus or minus 3 sigma. Well, we know what's going on. We know that there's a distribution of possible values. We have a distribution here. 3 sigmas takes you way out there. And we know that all the data is going to be in here. And there's really less than a 1% chance that you're going to get a data point outside the 3 sigma limit, outside this range of data. Well, if you do get one out of there, what happens is you say the machine is out of control. You stop the machine and you go call a repair service, and they come and they tune it up and they bring it back to control. Now, yes, that means once in a while, once in every 99 times or so, you might get something out of control that isn't out of control. If by accident goes out there, well, they have procedures for that. They might want 3 in a row that's out of control before they'll call in a repair team if it costs a lot. If it's just means shut the machine down and look at it, takes a few minutes, well, they're willing to do that. Even once in a while, they do it for nothing. They're willing to do it to make sure they don't manufacture bad parts. So what we have is the 3 sigma limit when things are out of control. Okay, now that's when we're talking about data. But if we're talking about averages, that is, if I go ahead and I manufacture a whole stuff for a whole day, and at the end of the day, I just take the average of everything I manufactured for the day. The 3 sigma limit, if I'm talking about ligma, I have to be careful. The standard deviation of the average is not sigma. It's sigma over the square root of n being how many observations I did that day. So when I talk about the interval, I mean mu plus or minus 3 sigma over the square root of n. So I'm checking with x bar, the average for the day. I would use the 3 sigma over the square root of n limit. It's also called the 3 sigma limit, but we must be careful. Don't let the wording throw you. People will say the 3 sigma limit, but it's really the 3 sigma over the square root of n if you're dealing with averages. Here's an X control chart. This is what would be given to the process engineer. And what he does, we've plotted mu, that is, we know the process has an average of this in its history. And we know the 3 sigma limits is here and here. Those are the 3 sigma limits. That means this machine has been producing parts within this range, sort of looking, if I were to draw a picture, it would be sort of You know, if you can draw something like that, producing parts like that for quite some time now. And the process engineer is supposed to look at the parts, and you get, each day he puts something down on a chart, and he gets pictures like this. Every day he puts another tick mark down as to where the observation was. Now all of a sudden, this is what happens. He finds that. Boom. Whoops. What's happened is we've gone off. Okay, what might be the case is that the machine, the process, is out of control, and what's being produced is not what's usually produced. Stop the machinery, call in the crew, and let them check out the machine. Maybe it's an accident. Maybe there's nothing wrong with the machine, and the very next part would be here. And that's okay. They'll just say, okay, keep going. If the machine needs tuning, they'll fix it, and from then on, you'll get numbers that are back within the control limits. That's what happens. That's what the process engineer does. If he's working with X bar, has an X bar chart, then he'll only put one mark each day. And this is the same mean, but the upper and lower control limits are much tighter. And they're drawn to the same scale here, but the numbers are much smaller because the average, the sigma is sigma over the square root of n. And this is 3 sigma, and this is minus 3 sigma over the square root of n. And average values will, again, look like this, an X bar chart. If ever a value comes outside the lower control limit or upper control limit, below minus 3 sigma over the square root of n or above 3 sigma over the square root of n, the engineer will stop the system, call in the repair crew, and check the machinery. That's called process control. Okay, let's take an example. Johnny's been sent to school. He was doing fine all year. He had an average of 90 with a standard deviation of 5. Yes. 5. So then you have a 15 plus or minus is the 3 sigma limit. And so his father says, okay, I expect you to have grades within this range. Now, Johnny is a junior, and he's just joined a fraternity. Whoops, if he joined a sorority, he certainly would have lousy grades, but he's just joined a fraternity. And the father wants to check up and see that nothing goes wrong with his grades. So he takes his grades as he gets them and he plots them on an X chart, because he has only one grade each time. It's on an X chart. And in the beginning of the semester, Johnny's doing fine. And all of a sudden, boom, Johnny is out of control. His grade is too low. His father calls him in and checks and says, now what's going on here? Have you been studying? Have you been partying too much? Why are you... He corrects the situation. He tries to fix if there's anything broken. If there's just an accident and Johnny wasn't feeling well one day, well, okay, take an aspirin, go back in there and continue working. But if there's a trend and he's gone out of control because there's something wrong with the machinery, then he has to fix the machinery, kick him out of the fraternity, and get him back on track. Okay? Now, the same kind of thing, we could have an X bar chart, for instance. You could have an X bar chart for the teacher. What we do is, let's say, the teacher generally has classes that have 90, average of 90 on their exams, and the class standard deviation is 5, say. That's just to use it so I can use the same chart. And the department head wants to keep track of the teacher. And he sees, generally speaking, his classes have around 90 within 3 standard deviations. But all of a sudden he starts dropping, and the averages get smaller and smaller, and now the class average has gone below 75. And the department head calls him and says, what's going on here? Your grades are going down. The teacher's grades are going down, meaning your class is doing poorer. How come your class is doing so poorly? Well, is there something wrong with the way you're teaching? Is it your attitude, or you got problems at home? What's going on here? And you try and correct the process to get it back into control so that it's going around where it should be going around. That's process control. Now, specification is a little different. Let me talk about what specifications are. you have yourself a little place that you're going to screw in the screw. And certain screws will, if they're too small, will just slide right in, not hold anything. Other screws that are too big won't get in, and you'll strip the threads trying to get it in. But there's a range of screws that will fit in and hold what you want it to hold. Okay? The specifications would be the range on the screw that will allow it to fit. And if you go outside this range, there's no sense giving me that screw because I can't use it. So I will tell you my specification. You must sell me screws within this range. Too small, too big, don't send them. Okay? So I tell that to the part of my organization, my process engineer, and he puts on his process control, he puts specification limits. Here's the upper specification limit and the lower specification limit. If ever we go outside these, I can't use that part. Well, his process, it would be silly to have a machine that was producing parts that were out of the specification limit, because then the machine, the final product wouldn't work. So you tune your machinery in so that the machinery is within control inside the specification limit, so that even when it goes slightly out of control, that part's still not really bad, but it's bad enough for me to actually, unfortunately, people make the control limits really close to the specification limits. That's dangerous. You really should keep them in from the specification limit. But at any event, the control limit should always be inside the specification limit. If ever you tried to make something where the control limit was outside the specification limit, what would happen is that you'd be producing parts and you would let them go because the machine was in control, but they couldn't be used. Because a part that was in control, let's say this was the control limit and this was the specification limit. You'd occasionally get parts up here, here, and they're in control, but they're above specification. That means the car won't work because the screw won't fit, even though the machinery is in control. So you fine-tune your machine to make sure that the control limit is within the specification limit. Okay? The control limit must be inside the specification limit in order to keep the parts usable, not only the machine in control. All right? Now I want to talk about two kinds of this control stuff. Component-wise, where each piece has a specification. Okay? There's a specification given to each piece. And when you buy your parts, you make sure your pieces are within specs. Within spec. And there's some variability to the spec. You could have things a little smaller or a little bigger. Well, sometimes you can have them a little smaller, sometimes they're a little bigger. What you hope is that some of them are smaller and some are bigger, but when you put them all together, they come out right. That means if you have a big one, it matches up with a smaller one, the total length will be okay. The problem with this is that on occasion, you might get all small. See, this within specs, yet just on the small side of spec. And in that case, the total length will be too small to be usable. You could also get something which is a little bigger than it should be. Several of them bigger than they should be in a row. What's going to happen? The total length will be too big to be used. So when you do component-wise, you're hoping that big ones are offset by little ones, and that the offsettings counter each other, and in the long run, your automobile will run. That's what component-wise does. It's cheaper because you always have to look at each individual piece to see whether it's in spec or not. The other type of specification is product-wise specification. In product-wise specification, you want the entire product to work. Now, you don't really care about the specifications for each, but you have to have them in order to make sure the entire thing works. But it's all right if this one was hard to manufacture and you had a little extra leeway on this one, a bigger specification, you'd have to tighten up on the ones next to it. Make them really tight specifications to take care of the fact that this has a little bigger leeway. That's one of the good parts. One of the bad parts of product-wise is generally end up with having tighter specs on everything, because you want to make sure that when you add the limits of the specs together, you don't go over the limit for the whole product. The whole component must work. The whole car must work. It is pretty sad if I have a car in which every piece that I bought from my subcontractors was within specifications. I couldn't go back to any of my subcontractors and say, you're out of specifications. But when I put the car together, it fell apart. And the reason it fell apart was that the hole maker made me a hole that was a little small today, but it was within spec. And the screw manufacturer made me a screw that was a little big today, but it was within spec. And I couldn't get that screw into the hole, or vice versa. The hole was too big, the screw too small. I put it in, but later on when someone was driving, the screw fell out. Both within specs, but one on the high side, one on the low side, and they didn't quite match up. The spec should be that the product works. That's not so easy, okay? However, it is the Japanese philosophy. Japanese philosophy says that the product is what counts. We want to make the product work. If we have to have higher specifications on each individual part in order to do this, well, so be it. It is important that the whole product work, and the reason for that is what's called, in their philosophy, saving face. It is, in the Japanese custom, it is, saving face is, if I build a car and I send it out, a Japanese person builds a car and sends it out, and that car doesn't function right, the person that bought it is going to be, he's going to think poorly of you, and you will lose face. You will lose face because your product is inferior. You might have to commit hara-kiri. It's not worth it. So you make the thing work right because you don't want anyone complaining. So you do very hard to make quality stuff. Nobody complains. That's the Japanese philosophy. It's an age-old custom not to lose face. In the American philosophy of quality control, the bottom line is what counts. The bottom line. This is a business. This isn't I like people driving my car. It's how much money can my company make when I build this car. And what happens in that case is the following. I can make better specifications, tighter specifications, but I have to pay more for that. I can make a better quality car, but I have to pay more for that, and that means the customer's got to pay more, and I will lose customers to some other company. So what I have to do is make my car as cheaply as possible so that I can get the money in and make as big a profit as possible. Well, now people come to me with the following problem. Hey, unless we increase the specifications and therefore make less money, we will have to repair the car because it's going to need repair when it goes out. I have to say, okay, American businessman, how much will it cost if I fix it now, put in better quality? How much will it cost? What's my total profit for the year if I have a better car? My total profit. That takes into account I'll lose sales and I'll get less money, profit, so on. Okay, what is my total bottom line profit at the end of the year if I make a poorer quality car and I send it out? Now, some of them will work. No one will ever complain about them. Some of them they'll complain, they'll bring it in to be fixed. Our people will have to fix it. We'll have to pay to have it repaired. Sure, it costs more to have it repaired later, but maybe not that many will do it. Well, what it'll cost if I have it done that way? And they come in, they figure it out. Now, if it turns out that it's cheaper for me to repair some of these, the cars that need repair, after they go out, rather than fixing them before they go out, the bottom line philosophy says, send them out there. Now, I know they're not good, but anyone complains, we'll fix it. Bottom line philosophy. Nothing is put in there for goodwill, because goodwill is very important. Person buys a car and they have to bring it back to the dealership every 2 weeks to have it fixed. They're not buying that brand of car ever again. I know, I've been there. You don't do it. You just don't buy that brand. No matter what they say on the screens on television, how wonderful their quality is now, you don't believe them. You have been there. So they don't take that into consideration because that's 5-10 years down the road. They may not be in business then. They're interested in the bottom line this year. Now, the Japanese philosophy does take that into consideration. And what's done there is that there's a loss function. A loss function. And what that means is that In this loss function is put all sorts of things. Saving face is put in, buying my car again for me or someone else is put in, how much it costs to repair it, how much profit I make on this car. All that stuff is put in as an ingredient into this big loss function. And then I find the bottom line, what it's worth to me. But in there are the intangible things like goodwill and whether the customer is going to come back and buy another car. Everything is taken into consideration. And unfortunately, in many of our American situations, we don't do that. We should, definitely should. It is very important to take everything into account and not just look at the profit this year, but look at the long run profit. Look at other things. Okay? The Japanese have it over us right now, and we are improving our quality. Now, let me go out on a limb and make a prediction, because I'm a statistician, and statisticians have to go out on a limb occasionally. I'd love to be able to say that American companies realize that the Japanese are getting ahead of us because they're paying more attention to quality, and therefore we have to pay more attention to quality. That is true. We are doing it. We are improving the quality of American cars. But I'm going to go out on a limb this way. The Japanese are seeing that tariffs and all sorts of things are reducing their profit. They, by making such good quality cars, are losing money to the Americans because the Americans can make a cheaper car and get away with it. So what's going to happen is I feel bad saying this, but I think what's going to happen is that the Japanese quality is going to come down to meet. Our quality is going up to meet the Japanese, but their quality is going to come down to meet the American quality, and eventually they'll be on par, where the quality of all the cars will be the same, whether they're American or not, and unfortunately, it's not going to be the best of quality. Okay? See you next time.